Hello everyone, thanks to the organizer. I will talk about coupling physics-informed neural network with OpenFOAM, and this is a work in collaboration with Giovanni Stabile and Gianluigi Rozza. So we are from MATLAB CISA, Italy, in Trieste. I'm a postdoctoral researcher in the mathematics department. Okay, so just to be on the same page, regarding the work, so a brief introduction of reduced order model. So reduced order model is a numerical scheme which to expedite any general numerical simulations. So there are three types of reduced order model in general. So one is projection-based reduced order model, data-driven approach, and there is a hybrid approach in between. So if we look at projection-based reduced order model, so we try to project the governing equations on a reduced space and try to solve that equation in the reduced coordinate. So we have, so there is a dedicated platform called Ithaca AP. So you can have a look in our MATLAB group. So it's an OpenFOAM based platform. And all the linear algebra packages required for the projection-based reduced order model are there in that package. So then next is the data-driven approach. So this is quite simple. You can generate the data from any solver and then use some kind of data-driven schemes to approximate your parametric space or temporal domain, anything. So there is something in between, so which is the hybrid approach, which is a marriage between these two, projection-based reduced order model and data-driven approach. And I have developed this. So inspired, there is a lot of inspiration coming from physics-informed neural network, so which has become recently very promising. So if we look at the timeline, so back in 2017, majority of the work was like projection-based reduced order model, I told. And from 2017, this data-driven approach came into the picture for approximating the parametric space. And from 2019, this seminal paper came out on physics-informed machine learning. So where you actually try to circumvent the sparsity of data by introducing some physics that is coming from governing equations. And then from last year, we started to think why use some kind of automatic differentiation or some conventional schemes that has been used in physics-informed neural network. Why don't we use the governing equations directly from the physics solvers that we have? So be it OpenFOAM or anything. So, so this is the idea now. So we have several benefits if we for the forward solvers like OpenFOAM we have. So first of all, it is physics based. It is good for well-posed problems, but it poses some issues when we need to introduce it for different repetitive tasks like design or control or something. But on the other hand, if you go to the neural network based or deep learning based approaches, so they are data driven, good for ill-posed or inverse problems, and for repetitive tasks, it can quickly do your job. But its accuracy depends on the richness of the training data set. So now we introduced a new method came up in that I talked about physics-informed neural network that circumvent the sparsity of the data. So what it does, so imagine T and X as an input and U as an output. So if there is an algebraic relationship between U and with T and X, because there is because neural network formulations is there between the input and output, and from that formulations we can compute the temporal and spatial derivatives, and the general governing equations can be considered as an additional loss penalty additional to the data-driven part. So now our objective is that, so instead of computing those derivatives of those U with respect to T and X, those spatial and temporal derivatives, instead of relying on automatic differentiation, we can get it from any forward solvers that we have. So that's the straightforward objective. So if any industry is using any forward solver for solving their problems, and they want to use some kind of machine learning based approach for machine learning based approach for solving their inverse problems or any optimization problems. So they should use that forward solver state array. So that's the objective. And you can use both full order simulation as well as projecting them on a reduced space as well. So this is what I'm talking about, full order simulation. So you can discretize a governing equation in any form. So like any spatial discretization, any temporal discretization. And what you do, you project them on a reduced space. So I'm not going in detail of them. So there are dedicated literature for that. And the projected governing equation look like that. So you can either use the full order simulations or reduced order simulation and use them as a residual in your pin solver. So now question is that how can we couple pin and any forward CFD solvers? So it's irrespective of OpenFOAM. So what are the issues we possess while coupling any kind of forward solvers, be it full order or projected on a reduced schemes, and coupling with some kind of machine learning solver we have, ANN or LSTM, whatever. So main issue is that our forward solvers, like in our OpenFOAM, they are coded in Open C++ or something like that, and pin solver is coded in PyTorch or TensorFlow. So what happens? The computational graph breaks because if these two solvers are in separate environment, and that creates a challenge for gradient-based optimizations. So what do I mean by that? So basically in pin, as you know, so we need to compute gradient at several layers. So first of all, you have to compute the gradient while computing the spatial and temporal derivatives. And another directions, we need to compute the derivatives where we, in the backpropagation algorithms, where we need to compute the gradient of the loss term with respect to the neural network hyperparameters. So the first terms, we got rid of it because we are now borrowing these derivatives from the OpenFOAM. And for conventional pin, we still need that. But for the dispin, in our case, we don't need them anymore. But on the other hand, this gradient of loss term with respect to the hyperparameters, we still have to compute. And since there is no computational graph retained, because the code is now at two separate environments, this loss term which is coming from OpenFOAM, and that so there is no formulation of L with respect to P, so we cannot get this derivative using automatic differentiation. So we have to do this derivative using some finite difference or something of that sort, and which makes it very expensive. So now idea that how can we compute this derivative of loss term with respect to the hyperparameter very easily using finite difference if it is coming from any external CFD solvers. So as you can see, there are two types of loss term. One is based on equations and one is based on data. So data-based part is fine because it's a Y predict is an outcome of the machine learning. As you know, why like if you have an input like T, and if you have then out of the neural network, you get some predictions, and you try to compute the distance with respect to their actual values, and that's how the data-driven loss term is derived. On the other hand, so you compute the Y predict, pass it to a CFD solver, and you get the residuals, which is R square here, Ri square here, and you try to minimize this loss term. So now let's look at how do we compute this derivative with respect to parameters. So that's the objective now for the backpropagation algorithm. So now if you take a derivative of R square with respect to parameters, it becomes 2Ri del R by del P. And also if you make a further chain rule, so it becomes del R by Y predictions, which is the outcome of the neural network, and del Y predictions by del P. And now problem is that if you take this, if you compute this one using finite difference, it will be extremely expensive because it is a dense matrix. And because on the other hand, if you compute these two matrices using finite difference, they will be much cheaper, because this residual is like a residual of momentum or continuity or any kind of governing equations residuals, and Y predict is the physical variables like pressure or velocity or whatever terms you have. So this kind of derivative we always most of the time compute in CFD like Newton scheme or something like that. And also it's a sparse matrix because residual is locally dependent on the variables. So it can be easily computed. So we came from a very highly computing dense matrix to two simple computable derivatives because they are of their sparsity. And so these Jacobian you can update at every epoch iterations. So that's the idea. So even if you cannot compute using AD, so you can quickly compute them using finite difference by breaking them into two types of derivatives. So the new loss term that should go to your loss backpropagation should be this. And this is the algorithms that you can work for. And I applied it for a Burgers equation first, but this is not, the residual is not coming from OpenFOAM. This is coming from PyTorch. And I just wanted to check if the residual is detached, and if it is not detached, then my loss term is actually decaying similarly or not. So we checked that. So even if in both the cases, so if we implement the Jacobians the way I have discussed, and if the neural net and the network is not broken, in both the cases, loss term is quite well minimizing, and we can use this algorithm to couple it with any CFD solvers. So now let's come to OpenFOAM. So what we have done in OpenFOAM, as I have told, so we have a package called Ithaka MP. So that basically couple OpenFOAM with any kind of linear solver, linear algebra package for doing this kind of reduced order model techniques. So all the coding has been done in this Ithaka MP platform, and those interface coding, and then they have been coupled with another platform called PINA. So which is our PyTorch based physics informed neural network platform. You can have a look at this. These are the GitHub repository of those coding platforms. So idea in case of OpenFOAM is that so we get the residual in any way as an AX plus B, AY plus B format. So Y prediction is the outcome of the neural network. Say for any transient dynamic, say T is your input and say U is your output. And then you pass this U to the OpenFOAM and you get the residual in this format, AX plus B format. And your objective in PyTorch or in PIN platform will be to minimize this R. And that's how you will get the full solutions. So now problem happens if it is a linear equations, this type of governing equation R equal to AX plus B is enough because A is constant, B is constant. But because they are not function of their previous time step. But if it is a nonlinear equations, even A will be a function of previous time steps. So and you are borrowing this A and B from OpenFOAM, and you don't know those functional dependence because AN and BN are also function of previous time step. But since it is coming from OpenFOAM, you don't know those dependence, and you cannot compute the derivatives of loss term with respect to hyperparameter using any kind of automatic differentiation. So you have to go for finite difference. So you have to use the numerical the algorithm flow I have told earlier. So basically you have to compute this Jacobian del R by del Y predictions, and it can be very easily done in OpenFOAM context. So basically, if you do some mathematical manipulations on those residual and their dependence on the previous time step or current time steps, so you will get to know most of the terms become zero everywhere. So diagonal terms becomes n, and some of the terms you have to compute using finite difference, but it should be very easy. And another thing is that you don't have to compute this Jacobian at every epoch iterations. You can also compute the Jacobians at a step of the intervals, like 100 epoch iteration or 200 epoch iteration, something like that. So that is the idea. You can couple it with any kind of external solver like OpenFOAM. So if we look at some results, before going to results, so this is the coding platforms I have. So if you look at, so like this is the Ithaka MP platforms. We used PyBind for coupling the OpenFOAM with PyTorch platform. So our idea is to get the residuals out of it. So as you can see, we are using OpenFOAM functionals, and we get the A matrix as well as you can get the B vectors, and using the OpenFOAM functional, and then you convert it to the eigenvector and eigenmatrix and pass it to the OpenFOAM, and then implement the algorithm that I have told, and that is how you can minimize the residuals and you can solve your pin platform similarly. So first I have applied for a Poisson equations, and you can see that if you use only data points, like 2 spatial data points, I have used very coarse grid, but still you can see if you use only 2 spatial data points with predicted result is very bad if you don't consider any physics. But if you consider physics, then the predictions is very comparable with the actual results. And here you only consider data at some spatial locations, and all the spatial locations, the governing equations has been satisfied, and the residual has come from OpenFOAM. Also, if you look at some nonlinear equations where those kind of corrections will be required, if you look at the results like this, so is the CFD simulations is something like that. So far we are at the initial stage. We have knowingly introduced more diffusions. And also if you consider all the data points and physics has been solved everywhere, so both are almost same. And if you use some less data and most of the physics has been solved everywhere, so this is the result for that. And if you don't use any physics, only data points, then it is a complete garbage. So basically, and this is somewhat similar to my benchmark cases, but still there are some discrepancy. I mean, still there are a lot of improvement yet to be done, but yet it is still working much better than if there is no physics coming out and helping the data to approximate the physics. And but this is a work in progress, but we have somehow implemented our algorithms for coupling with any external data solvers. And that's it. And this is my future work. And we are coupling EtherCAB with PINA. So EtherCAB already have those projection-based reduced order models. And our objective next steps to couple them with physics-informed neural network, explore different types of neural networks. And we will in future apply for large-scale applications like multi-physics and multi-species problem like annealing furnace. Yeah, thank you. Thank you. If you have any questions, you can ask me.
Okay, thank you for your last talk. Any questions?
Thank you for your brilliant work. I want to ask something about that. I have seen some comments say that PINS has the ability to simulate something like a high-dimensional problem, something like a 100-dimension Poisson equation, but they have some limited about the simulate a very complex geometry problem. So
Exactly.
do yours sorry?
Yes, please go ahead.
My question is that your work coupling of the finite volume method and PINS can make their improve the ability to simulate the complex geometry problem?
Yes, so that's our hope is. So far we have applied it for very easy cases. So here idea is that offloading all the tasks with the forward solvers like OpenFOAM, you are using OpenFOAM for solving any kind of forward problem. So idea is that you take the residuals and try to minimize it in the optimization setting of the machine learning. So you don't need to compute those AD for all the derivatives for all the boundary conditions and initial conditions. So here everything is coming from OpenFOAM, so which you have already used for the forward solver. So that is our hope, that it should be useful for solving complex geometry and large scale problems. Another advantage that we are doing, so main issues of this any kind of in general machine learning platform is that, so the cost of dimensionality. So even if the burden of optimizing lot of loss terms becomes huge for large scale problem, so then it will be very difficult to minimize the governing residuals, the governing equations residual at every point. So that's why we introduced this first project them on a reduced space, say like this annealing furnace will may have some millions of degrees of freedom. And then once you project them on a reduced space, so you have some in the order of 100 or 200, and then use P. So that's the idea. So it's a coupling between, already we have some linear algebra package like is singular value decomposition or something. First project them on a reduced space, minimize the load of the optimization, and then apply P. So these are the two ideas. One is that use same the forward solver that you have, and second thing is that you first project on reduced space and then optimize using PIN.
Okay, thank you very much.
Mm-hmm.
Hello.
Yes.
About the loss part, the partial L over partial Y prediction, and you use the matrix deduction.
Yes.
Yes. Is it part consistent with the discrete adjoint method?
So I'm not aware of that, but here idea is that I have to compute the residual loss term with respect to the hyperparameter. So if I do this, it will be extremely expensive, because hyperparameters are, it will be a dense matrix, like because R is globally dependent on P. Because like residuals that is coming out of the OpenFOAM or any kind of CFD solver, and your hyperparameters, like it's dependent on the entire vector. So it will be a very dense matrix. But if you break them into two parts, so it will be easier to compute these two terms itself. And this one I did it using finite difference. I did not use any discrete adjoint or something like that. So but I'm not aware of that part. So but that's the key idea here.
Okay, thank you.
But yes, but if you have some adjoint solver in your solver, so it is easier to compute, because finite difference is still expensive. But if you have some adjoint solver, so I think OpenFOAM do also have, but I'm quite sure other existing open source solvers do have. So main idea is to compute this. So if you have adjoint solver, you can easily compute it, and you can even further accelerate your pin solver. But for now, I have used finite difference. But you can, adjoint solver will be much better to compute this. Yeah.
Okay, thank you again.